Hello everyone and welcome back to our channel. In today's video, we are going to talk through a short history of nearly everything by Bill Bryson, published in 2003. But before we get started, make sure you hit that subscribe button and turn on the notification bell so that you never miss any of our upcoming videos. Okay, let's get started. In the introduction of A Short History of Nearly Everything by Bill Bryson, the author discusses the intricacies of existence and the role of atoms in creating and sustaining life. He notes that atoms are mindless particles that do not have the ability to care, yet they work together to keep individuals intact. Bryson highlights the uniqueness of atoms, as they are the same particles that create everything else in the universe. He also explores the extraordinary chain of biological events that led to human existence and emphasizes the fragility and impermanence of life on Earth. Moreover, he reflects on his childhood fascination with science and his desire to understand how scientists uncover the secrets of the universe. Bryson's book also discusses the concept of the Big Bang and the beginning of the universe. It explains that the singularity, the starting point of the universe, was a tiny, compact spot with no dimensions. When the universe began to expand, it created space as it went instead of spreading out into existing space. The discovery of cosmic background radiation is considered evidence of the Big Bang. While inflation theory suggests that the universe underwent a sudden expansion shortly after its creation. This expansion allowed for the formation of stars and galaxies. In Bryson's book, he concludes with mentioning the possibility of multiple universes and the importance of precise values for the existence of our universe. He also discusses the concept of the universe's size and the curvature of space. The three possible universes are described as closed, open, and flat, with the critical density being the ideal state where gravity holds the universe together. However, it is noted that one can never reach the edge of the universe due to space bending in relation to Einstein's theory of relativity. The book also explores the discovery of Pluto's moon and the uncertainty surrounding Pluto as a planet. The excerpt concludes with a discussion on the vastness of space and the hypothetical journey to the edge of our solar system. Bryson's book also mentions recordings of the Voyager 1 and 2 spacecraft, which currently hold the record for the fastest speeds achieved by any human object, flying away from us at about 35,000 miles per hour. They were launched in 1977 when Jupiter, Saturn, Uranus, and Neptune were aligned, enabling them to use a gravity assist technique to propel themselves from one planet to the next. However, even with these speeds, it took the Voyager craft years to reach Uranus and Pluto. The vastness of space becomes evident when we consider that our solar system fills less than a trillionth of the available space. The distances are so vast that even if we tried to draw the solar system to scale, it would be impractical. Beyond our solar system, Bryson mentions that while the probability of other advanced civilizations existing is high, their sheer distance from us makes any form of contact or interaction highly unlikely. Robert Evans is a talented amateur astronomer who has a knack for memorizing star fields and has discovered 36 supernovae. He leads a modest life in a bungalow on the outskirts of Sydney, with a homemade telescope in his storeroom turned observatory. Evans' discoveries have contributed to our understanding of the universe, but he is not alone in his pursuits. Fritz Zwicky is an eccentric astrophysicist who was the first to propose the idea of neutron stars and supernovae. However, his ideas were largely ignored by his colleagues. Supernovae, while rare, play a crucial role in astronomy as they can be used to measure the expansion rate of the universe. Today, with the help of computer technology, even amateurs are able to find supernovae. While a nearby supernova would be catastrophic, the chances of it happening in our corner of the galaxy are slim. Supernovae are essential for the creation of heavy elements, without which life as we know it would not exist. English cosmologist Fred Hoyle explained how supernovae forged carbon and iron and other elements necessary for our existence. He also coined the term Big Bang and proposed a steady-state theory of the universe. Hoyle's work, along with his collaborators, showed how heavier elements are formed in supernova explosions and eventually form new solar systems. The formation of Earth started around 4.6 billion years ago when gas and dust accumulated and formed the Sun. Over time, planetesimals collided and grew, ultimately resulting in the formation of our planet. The early Earth had an atmosphere mainly composed of greenhouse gases, which prevented the planet from freezing over. Life on Earth began to form in this hostile environment, and eventually, humans came into existence. The French Royal Academy of Sciences expedition in Peru in 1735 aimed to measure the circumference of the Earth. This expedition faced numerous challenges and setbacks, but it contributed to our understanding of the Earth's size. Edmund Halley initiated a wager with Robert Hooke and Christopher Wren to understand why planets orbit in ellipses. Halley sought out Isaac Newton for help, who promptly provided the solution. Newton's brilliance was undeniable, although he had unconventional beliefs, such as alchemy and heretical religious practices. His encounter with Halley led to the discovery that planetary orbits are ellipses. Newton's famous work, The Principia, made him instantly famous and earned him many accolades and honors. The book explained mathematically the orbits of heavenly bodies and identified the force of gravity. Newton's three laws of motion and his universal law of gravitation were at the heart of the Principia. Newton's laws explained many things such as ocean tides, planetary motions, and the trajectory of cannonballs. One controversial revelation from the Principia was the suggestion that the Earth is not perfectly round, but rather slightly oblate due to its spin. This challenged the assumptions made by those trying to determine the size of the Earth. Several attempts were made to measure the Earth's circumference, including Richard Norwood's method involving trigonometry and Jean Picard's method of triangulation. Ultimately, Bouguer and La Condamine's survey in the Andes confirmed that the Earth was fatter at the equator. Additionally, Newton's theory predicted that a plumb bob near a mountain would incline slightly towards it, which led to Maskelyne's successful scheme to weigh the Earth. This involved finding a mountain of regular shape to calculate its mass and the universal gravitational constant. Charles Mason, an astronomer and surveyor, was chosen for this task. Legendre, despite facing numerous setbacks, continued his journey to India to observe the transit in 1769. However, he was once again thwarted by a cloud that covered the sun for the entire duration of the transit. On his way back home, he faced further hardships, including contracting dysentery and a near shipwreck. When he finally returned, he discovered that his relatives had declared him dead and plundered his estate. In comparison, Britain's observers faced milder disappointments. Mason and Dixon's ship was attacked, preventing them from observing the transit in Sumatra. They observed inconclusively from the Cape of Good Hope and later settled a boundary dispute, creating the famous Mason and Dixon line. Meanwhile, Maskelyne and other astronomers concluded that the 1761 transit measurements were a failure. Captain James Cook successfully observed the 1769 transit and later charted Australia. Michel and Cavendish made significant contributions to astronomy and the understanding of gravity, with Cavendish's experiment resulting in the first measurement of the Earth's weight. The book discusses the contributions of James Hutton and John Playfair to the field of geology. Hutton's book, Theory of the Earth, challenged the prevailing beliefs at the time and proposed the idea of deep time and uniformitarianism. However, Hutton's work was not widely recognized until Playfair simplified and popularized his theories in his book, Illustrations of the Huttonian Theory of the Earth. The book also mentions the formation of the Geological Society in 1807, which further contributed to the growth and popularity of geology as a science. Mrs. Buckland and her husband, Reverend Buckland, conducted an experiment involving their tortoise to prove that their findings about Cheirotherium were accurate. Despite Charles Darwin's criticisms, Lyell found Buckland inspiring and they even went on a tour together. Lyell's book, Principles of Geology, published from 1830 to 1833, solidified and expanded upon Hutton's earlier theories. The geological controversy of the time centered around catastrophism versus uniformitarianism. While catastrophists believed in abrupt cataclysmic events shaping the Earth, uniformitarians argued for slow, gradual changes. Lyell believed in uniformity and his influence was enormous. However, he disregarded certain ideas that were ultimately proven correct, such as mountain formation and the existence of ice ages. The Great Devonian Controversy was another heated dispute among geologists regarding the categorization of rocks. Overall, Lyell's theories shaped geological thinking for many years and even influenced Darwin. The dating of the Earth was a challenge, with various attempts made by scientists such as Archbishop Usher and Edmund Halley. Buffon's experiment estimated that the Earth was between 75,000 and 168,000 years old, a radical idea at the time. By the mid-19th century, most believed the Earth to be millions of years old, but calculations made by Darwin caused further controversy. Lord Kelvin, a brilliant scientist, became interested in the issue and would play a significant role in the age of the Earth debate. Kelvin, a remarkable Victorian figure, had a prolific career in the physical sciences. He made significant contributions to refrigeration, absolute temperature scales, telegrams, and navigation, among other things. However, he struggled with accurately calculating the age of the Earth. Despite revising his estimates several times, Kelvin's calculations did not align with the fossil evidence, which increasingly pointed towards a much older Earth. Meanwhile, during the same period, the discovery of dinosaur bones in America and the work of paleontologists like Georges Cuvier and Mary Anning in Europe were challenging religious beliefs and providing insights into extinction and geological history. Their discoveries highlighted the importance of fossils and the need to better understand the formation of rock strata. Mary Anning, a skilled amateur paleontologist, spent years excavating a plesiosaur and providing valuable drawings and descriptions. However, she lived in poverty and was often overlooked in the field of paleontology. Gideon Algernon Mantle, a country doctor, made an important discovery of a herbivorous, reptilian tooth that belonged to a previously unknown animal. Mantle faced difficulties in getting recognition for his findings as another dinosaur had just been discovered by the Reverend William Buckland. Richard Owen, a prominent paleontologist, took credit for many of Mantle's discoveries and persecuted him relentlessly. Mantle's life ended tragically, and Owen's dishonesty eventually caught up with him. Owen later played a significant role in the creation of London's Natural History Museum. In the early days of the British Museum, visitors had to go through a lengthy process to gain admission and were not allowed to linger. Richard Owen changed this by welcoming everyone and putting informative labels on displays. However, he had personal rivalries, one of which was lobbying against a statue in memory of Charles Darwin. Edward Drinker Cope and Othniel Charles Marsh, two American paleontologists, had a venomous rivalry that changed the world of paleontology. They discovered numerous dinosaur species but often failed to note that some were already known. Cope wrote many papers and described new species but lost his fortune and died in poverty. Marsh finished his days in a splendid mansion. The age of the Earth was a topic of confusion among scientists, and it was Ernest Rutherford who provided evidence that the Earth was much older than previously thought. Chemistry transitioned from alchemy to a respectable science with Robert Boyle's publication. Hennig Brand discovered phosphorus while trying to distill gold from urine. Carl Scheele, a Swedish chemist, discovered 8 elements but was overlooked in favor of others. He also had a penchant for tasting chemicals, which eventually led to his death. Chemistry was in a state of discovery and confusion in the late 18th century, with scientists searching for unknown substances and theories to explain combustion. Antoine Laurent Lavoisier, a French scientist, played a crucial role in bringing clarity and method to the field. Despite not discovering any new elements himself, he made significant contributions by identifying oxygen and hydrogen and disproving the concept of phlogiston. Lavoisier's meticulous experiments with rusting objects led to the concept of conservation of mass. However, his affiliation with the despised Ferme Générale and involvement in the French Revolution ultimately led to his execution during the Reign of Terror. Chemistry in the 19th century faced challenges due to the lack of equipment and the perception of it being a science for businesspeople rather than gentlemen. Count Benjamin Thompson, later known as Count von Rumford, played a crucial role in establishing the Royal Institution and promoting chemistry in England. Humphrey Davy, a chemist at the Royal Institution, discovered several elements using electrolysis. Avogadro's principle, which stated that equal volumes of gases contain identical numbers of molecules, was also a significant development during this time. However, due to the lack of organization in the field of chemistry, Avogadro's breakthrough was not widely known until the mid-19th century. Chemistry in the second half of the 19th century was in disarray until Dmitry Mendeleev came onto the scene in 1869. Born into a large family, Mendeleev's mother worked to ensure he received an education. Mendeleev eventually became a professor at the University of St. Petersburg and began to arrange the elements in a way that had not been done before. He created the periodic table grouping elements by their properties and atomic weights. Mendeleev's table proved to be a significant breakthrough and provided order and clarity to the field of chemistry. In addition, the discovery of radioactivity and the radioactive decay of elements further expanded scientific understanding. Marie Curie made significant contributions to the field and helped establish the Radium Institute. However, radioactivity also proved to be dangerous, causing illness and even death for those exposed to it. In 1891, Max Planck discovered that the work on entropy had already been done by J. Willard Gibbs. Gibbs, although relatively unknown, made significant contributions to thermodynamics, specifically in his papers on the equilibrium of heterogeneous substances. These papers explained the principles of thermodynamics and their application to various areas such as gases, mixtures, and chemical reactions. Despite his brilliance, Gibbs chose to publish his work in an obscure journal, and as a result, it went unnoticed by many prominent scientists, including Planck. Meanwhile, in Cleveland, Ohio, Albert Michelson and Edward Morley unknowingly undermined the concept of the luminiferous ether through their experiments. The Michelson-Morley experiments showed that the speed of light remained constant in all directions and at all seasons, challenging Newton's laws and setting the stage for the quantum age. Finally, in 1905, Albert Einstein, an employee at the Swiss Patent Office, published several groundbreaking papers, including the special theory of relativity and the theory of mass-energy equivalence, E equals mc2. Einstein's work revolutionized our understanding of energy, light, and the universe. His special theory of relativity dealt with things moving in an unimpeded state but failed to account for the effects of gravity. His general theory of relativity, published in 1917, addressed this issue and stated that space and time are relative to the observer and the object being observed. However, understanding relativity was challenging due to its non-intuitive nature. Popularizers of science attempted to make the concepts accessible, with one successful example being Bertrand Russell's book, The ABC of Relativity. Einstein's general theory of relativity also proposed that the universe must be expanding or contracting, but he added a cosmological constant to counterbalance the effects of gravity, which he later considered a mistake. Edwin Hubble, an astronomer, discovered that distant stars were moving away from us, providing evidence for an expanding universe. Cepheids are elderly stars that have moved past their main sequence phase and have become red giants. They burn their remaining fuel in a way that produces a rhythmic brightening and dimming. Edwin Hubble measured selected points in space and showed that the universe consisted of many independent galaxies, and that the universe was expanding in all directions. Atoms, on the other hand, are small, numerous, and practically indestructible. John Dalton established the idea of atoms and their relative sizes and characteristics, which became the basis for modern chemistry. However, the existence of atoms remained hypothetical for a century after Dalton proposed the concept. Ernest Rutherford played a crucial role in the early development of atomic theory. His most groundbreaking work came from his realization that atoms were mostly empty space with a dense nucleus at the center, which he discovered through his experiments with firing alpha particles at gold foil. This finding posed immediate challenges, as it contradicted conventional physics and raised questions about the stability of atoms. Rutherford's colleague Niels Bohr later developed the theory of quantized orbits for electrons, while Rutherford proposed the existence of neutrons in the atomic nucleus. The delay in discovering neutrons was significant, as their understanding was critical to the development of atomic bombs. The behavior of electrons, which could behave as both particles and waves, also perplexed scientists during this time. In the 1920s, quantum mechanics emerged as a new branch of physics, with competing theories by Erwin Schrödinger and Werner Heisenberg. Heisenberg's uncertainty principle stated that the electron is both a particle and a wave, and that the more accurately one measures its position, the less accurately one can measure its momentum, and vice versa. This led to the conclusion that electrons do not exist until they are observed, and that they can exist in multiple places simultaneously. Quantum theory presented a world that was vastly different from what had been previously understood. Physicists struggled to comprehend its strangeness, and even Albert Einstein disputed its fundamental principles. Quantum physics introduced a level of untidiness that required two separate sets of laws to explain the behavior of the universe: quantum theory for the small scale and relativity for the larger universe. Despite its challenges, progress in understanding the atom continued, leading to the development of atomic bombs. At the same time, scientists were investigating the age of the Earth and its composition, which was impacted by the use of lead in gasoline. The harmful effects of lead were discovered, along with its contamination of the environment. Thomas Midgley Jr., the discoverer of lead's anti-knocking properties, also invented chlorofluorocarbons, CFCs, which were later found to have harmful effects on the ozone layer. Radiocarbon dating, invented by Willard Libby, allowed scientists to accurately determine the age of organic remains for the first time. However, there were flaws in the method, including a 3% error in the decay constant and the potential for contamination. Arthur Holmes developed a method to date rocks using uranium lead decay, determining that the Earth is at least 3 billion years old. Claire Patterson further refined the age of the Earth using meteorites and also exposed the dangers of lead pollution in the atmosphere, eventually leading to the removal of leaded gasoline. The United States banned lead in indoor paint much later than Europe, and lead solder was only removed from American food containers in 1993. The Ethyl Corporation, which was involved in the production of leaded gasoline, continued to dispute the harmful effects of leaded gasoline on human health and the environment until 2001. The author discusses the importance of Earth's atmosphere for supporting life. He explains how the atmosphere provides warmth, protection from cosmic rays, and regulates temperature. The Earth's atmosphere is being divided into 4 layers: the troposphere, stratosphere, mesosphere, and ionosphere. The troposphere is the layer closest to the surface and contains most of the atmosphere's mass, weather, and oxygen. It is relatively thin, only about 10 miles thick at the equator. Beyond the troposphere is the stratosphere, followed by the mesosphere, and then the ionosphere. As one ascends through these layers, the temperature fluctuates drastically. The highest layer, the thermosphere, reaches temperatures of 2,700 degrees Fahrenheit. The human body is not designed to function comfortably at high altitudes, and even experienced mountaineers face a host of challenges. Bryson's book discusses various phenomena related to altitude, temperature, air pressure, and weather patterns. It explains how bodily distress can occur at high altitudes, with even fit individuals becoming severely debilitated. It also describes the relationship between altitude and temperature, noting that the temperature drops as one ascends. The density of molecules in the atmosphere is discussed, with sunlight energizing atoms and increasing molecular collisions, thereby releasing heat. Bryson's book also highlights the mass and power of air, noting its ability to cause destructive storms and lightning bolts. The role of convection in driving atmospheric movement and creating weather systems is explained, as well as the Coriolis effect and its influence on wind patterns. The history of meteorology, including the classification of clouds by Luke Howard, is also touched upon in his book. Bryson's book describes water as a fascinating and essential substance that is often taken for granted. It explains that water is strange in its properties and behaviors, defying expectations based on other compounds. For instance, water expands when it freezes, allowing ice to float on water. Without this characteristic, life on Earth would be very different. Water molecules have a dance-like interaction with each other, constantly forming and breaking bonds. This allows water to flow and possess surface tension. Water is crucial for sustaining life, and our bodies quickly deteriorate without it. However, most of the water on Earth is poisonous to humans due to its high salt content. Overall, Bryson's book portrays water as a remarkable and vital substance that deserves our appreciation and protection. It discusses the proportions of salts and minerals in our bodies, which are similar to seawater, but emphasizes that we cannot tolerate them as an input. Consuming too much salt causes dehydration as water molecules rush to dilute and carry off the excess salt, leaving cells dehydrated. The majority of Earth's water is found in the oceans, with the Pacific Ocean alone holding over half of all ocean water. Only 3% of Earth's water is fresh, and most of it exists as ice sheets. Modern scientific interest in the oceans only arose in the 19th century, with the Challenger expedition in the 1870s marking the first organized investigation of the seas. Deep water exploration began in 1930 with Charles William Beebe and Otis Barton's dives in a bathysphere. The Piccard family later introduced the bathyscaphe, culminating in Jacques Piccard and Lieutenant Don Walsh's record-setting dive to the Mariana Trench in 1960. However, subsequent deep-sea exploration was hindered by lack of interest, opposition, and high costs. The author discusses the Navy's reluctance to fund further dives in the 1960s, which led to a demand for underwater exploration programs. Eventually, the Woods Hole Oceanographic Institution received funding to construct the Alvin submersible, providing better insight into the ocean floor. Nevertheless, our knowledge of the oceans remains limited, as our ocean floor maps are lower resolution than our maps of other planets. Investigative techniques in oceanography have been ad hoc, but advancements in technology have allowed for important discoveries. In 1977, the discovery of deep-sea vents off the Galapagos Islands revealed a living system independent of sunlight and oxygen, based on chemosynthesis. These vents also explain the mystery of why the oceans don't grow saltier with time. The vents act as filters, stripping salts from water and eventually releasing clean water back into the ocean. The dumping of radioactive waste in the oceans and the impact on marine life is mentioned. Radioactive waste was a common practice without much concern for its effects. The vastness of the ocean and its limited productivity make it easy to overtax. Overfishing, destructive fishing practices, and habitat destruction have led to the decline of many marine species, including cod and lobster. Biologists estimate that 90% of lobsters are caught within a year after they reach the legal minimum size. Despite declining catches, New England fishermen continue to receive tax incentives to acquire bigger boats and harvest more intensively. There is still much we don't know about life in the sea, with some naturally impoverished waters having more life than expected. There are millions of crab-eater seals, Weddell seals, emperor penguins, and Adelie penguins in the southern oceans around Antarctica, but the dynamics of how the food chain works in these areas are still unknown. The author points out that scientists have been trying to synthesize life since Stanley Miller's experiments in 1953, but have been unsuccessful. The book explains that proteins are a crucial part of life, but the chances of them spontaneously self-assembling are extremely low. Chemicals that make up life are not unique and can be found in many places. The emergence of life on Earth happened remarkably quickly and may have had external help, as the Murchison meteorite contained amino acids and sugars. Halley's Comet contains organic molecules, which could potentially provide the basic elements needed for life if they were to crash into a suitable location on Earth. However, panspermia, the theory that life originated from extraterrestrial sources, raises two issues. Firstly, it doesn't answer the question of how life initially arose, but merely shifts the responsibility elsewhere. Secondly, some adherents of panspermia entertain speculative ideas, such as the suggestion that Earth was intentionally seeded with life by intelligent aliens. These theories are considered to be on the fringes of scientific respectability. Despite the unknown origins of life, all living things on Earth share the same genetic code, dating back to a single ancestral event billions of years ago. The oldest marine sediments, found in Greenland, provide evidence of ancient life through chemical residues left behind by organisms, Bryson mentions. Scientists at the Australian National University in Canberra use a sensitive high-resolution ion microprobe to date rocks and study the Earth's geological history. The dawn of life, or something similar, is represented in the fossilized remains of stromatolites, which are structures formed by primitive organisms called cyanobacteria. Examples of living stromatolites can be found in Shark Bay, Australia, providing a fascinating glimpse into Earth's early existence. In about 2 billion years, cyanobacteria increased the level of oxygen in Earth's atmosphere, which allowed for the development of more complex life forms. However, these same cyanobacteria were almost wiped out by the organisms they made possible. Eventually, a new type of cell called eukaryotes emerged, which had a nucleus and other structures called organelles. This cell type evolved thanks to an invasion or capture of a bacterium by another bacterium, resulting in the development of mitochondria. Mitochondria are crucial for energy production and are necessary for complex life forms, like humans. Despite their importance, mitochondria maintain their own DNA and have different genetic characteristics than the cells they reside in. Eukaryotes eventually formed multicellular beings, leading to the development of organisms like humans. Bryson's book goes on to discuss bacteria and their role in our lives. It explains that bacteria inhabit our bodies and play a significant role in various functions such as digestion and nutrient conversion. The book also mentions bacteria's role in producing a large portion of Earth's oxygen. Bacteria are resilient and can survive in extreme environments, such as deep within the Earth. However, despite their prevalence and importance, bacteria were often overlooked until relatively recently. Ernst Haeckel proposed in the late 19th century that bacteria should be placed in a separate kingdom, but this idea was not widely accepted until the 1960s. Other poorly categorized organisms, such as fungi that were treated as plants despite their structural and functional differences. The division of life into three main domains, bacteria, archaea, and eukarya, was later discovered by Carl Woese. The divisions were initially overlooked or dismissed but gradually gained recognition among microbiologists. The world of microbes, including bacteria and archaea, is vast and diverse, comprising the majority of life on Earth. Only a small portion of microorganisms are harmful to humans, but can cause illness through various mechanisms, including utilizing mosquitoes as transmission vectors. The roles of the immune response to infection are explained, as well as the resulting illness that can occur. Sickness is a sensible response to infection as it allows for rest and allocation of resources to combat the invading pathogens. When the body is invaded by an infectious agent, the immune system mobilizes white blood cells to fight off the attacker. However, some pathogens have evolved to either quickly move to a new host or disguise themselves and evade detection. Infections can sometimes occur when harmless microbes enter the wrong parts of the body and cause havoc, such as in the case of necrotizing fasciitis. Misuse of antibiotics in the farming industry, leading to antibiotic resistance. Furthermore, the author raises the possibility that many diseases, including stomach ulcers and certain mental disorders, may have a bacterial component. Viruses, though not living organisms themselves, can cause immense damage by hijacking living cells to reproduce. The 1918 flu pandemic is mentioned as an example of the devastating impact of viruses. With air travel facilitating the spread of infectious agents, the author emphasizes the importance of being prepared for potential epidemics. He discusses the rarity of fossils and the challenges in their preservation, explains that only a small fraction of organisms are fossilized, as several conditions must be met, including dying in a place where the fossil can be preserved in sediment and being buried without exposure to oxygen. It is also unlikely for fossils to maintain their shape over millions of years and be eventually discovered. Less than one species in 10,000 makes it into the fossil record, and the record is heavily skewed towards marine creatures. A paleontologist named Richard Fortey, who specializes in studying trilobites, an extinct marine creature. The author then briefly mentions the discovery of the Burgess Shale fossils by Charles Doolittle Walcott and the significance of the fossils in revealing the diversity and experimentation in body designs during the Cambrian period. Gould's book, published in 1989, received critical acclaim but also faced backlash from scientists who didn't agree with his conclusions. In 1946, geologist Reginald Sprigg discovered ancient fossils in the Ediacaran Hills of Australia before the Cambrian explosion. His findings were initially rejected but were eventually recognized as the dawn of visible life. The Ediacaran organisms are soft-bodied oddities that lacked complex features. There is still disagreement about their classification and whether they are related to modern-day organisms. Some believe they were a failed experiment, while others see them as a precursor to the Cambrian explosion. The Burgess Shale fossils, which Gould wrote about, were later revised and found to be less strange and more explicable than initially believed. The Cambrian explosion is now thought to have been a result of an increase in size rather than the sudden appearance of new body types. This text describes the early development of life on Earth, particularly the evolution of land-dwelling organisms. It highlights the unique survival strategies of lichens, which can thrive in harsh environments by forming partnerships between fungi and algae. The history of human existence is relatively short compared to the history of the Earth, using a metaphorical 24-hour scale. The challenges that early land-dwelling creatures faced, such as the need to develop load-bearing structures and the ability to breathe air. The abundance of oxygen during this time facilitated the growth of large animals and plants. The author discusses the major extinction events in Earth's history, explaining that extinction is a natural process and that 99.99% of all species that have ever lived are no longer existent. Major extinction events, such as the Permian extinction which wiped out 95% of species, and the KT event which ended the age of dinosaurs. The causes of these extinctions are still debated, with theories ranging from global warming to meteor impacts. Some species were able to survive these events and prosper, such as turtles and small, furtive mammals. Overall, extinction is seen as a necessary part of Earth's dynamic history. The Natural History Museum in London is mentioned as being home to many impressive exhibits, including a giant diplodocus made of plaster and a skeleton of a barosaurus defending her baby. However, these displays are not made of ancient bones, but rather antique models. The author discusses the knowledge of dinosaurs being limited, with fewer than 1,000 species identified. Dinosaurs ruled the Earth for much longer than mammals, so either they were not very productive in terms of species or we have only scratched the surface. Even for the well-studied late Cretaceous period, 3/4 of all species may yet be undiscovered. It was recently discovered that dinosaurs remained numerous up until the time of the KT impact, challenging the belief that they were already declining. The back rooms of the museum are said to house a vast collection of specimens, including pickled animals, insects, plants, and bones, offering a glimpse into the richness of biodiversity. The mentioning of the moss department and the dedicated researchers spending years studying a single species or reorganizing entire genera demonstrates the meticulous nature of taxonomy. Mosses, while not commercially useful, are incredibly diverse and continue to surprise scientists with their adaptations and distribution. The Natural History Museum is described as a haven for those who appreciate the wonders of life on Earth. Fraser was successful in selling various plants and animals to English gentry, making a handsome living. Carl Linnaeus, who provided a workable system of classification for the overwhelming amount of new information. Linnaeus is known for his self-confidence and an obsession with sexual references in his descriptions. His system of classification, though not without flaws, brought order and simplicity to the naming of plants and animals. However, disagreements and revisions persist in taxonomy, and the true number of species on Earth is still unknown. The number of known species on Earth is vast, but our knowledge is far from complete. Estimates of the number of species for various groups, such as fungi, earthworms, insects, and plants, but notes that these numbers are just estimates and may be much higher. There is a lack of taxonomists and that many species are poorly described. Much of the time is spent sorting out old ones rather than discovering new ones. The small size of many organisms makes them easily overlooked, and the majority of microorganisms remain unknown, according to the author. Researchers often do not look in the right places, and many habitats remain unexplored. The author acknowledges that the world is vast and full of surprises and that it would be impossible to survey every corner and analyze every organism. But also emphasizes that this reality is incredibly exciting, highlighting the infinite capacity of the planet to surprise and the devotion of scientists to esoteric lines of inquiry. He then describes the intricacy and variety of human cells, their functions, and their interactions. Emphasizes the importance and complexity of cells in maintaining overall well-being, with each cell carrying the complete genetic code and knowing how to perform its specific tasks. The author also touches upon the history of cell study, from Robert Hooke's discovery of cells to Antony van Leeuwenhoek's reports on microscopic observations. Cells are made up of lipids, which behave differently at a microscopic level. He explained that the inside of a cell is a hazardous place, with DNA being constantly attacked and damaged. The texts mention that proteins within cells are very active, performing numerous tasks every second. Cells communicate with each other through messages sent by hormones and by directly interacting with their neighbors. Trillions of chemical reactions within a cell add up to create a harmonious organism. While cancer occurs when cells fail to expire and divide uncontrollably, cells die through apoptosis or programmed cell death. The book mentions that Darwin proposed the theory of evolution and natural selection, which challenged existing beliefs about the origins of species. It highlights the connection between Mendel's and Darwin's work and how they laid the groundwork for modern life sciences. The author discusses the complexity of genetics and how individual genes do not solely determine traits but rather work in cooperation with other genes to create a human being. Certain disorders are caused by dysfunctional genes, but for the most part, our fate and traits are determined by complexes of genes. The author also delves into the complexity of proteins, which are influenced by factors like shape and function, mentioning that the human genome is likened to a parts list, whereas the proteome, which creates proteins, is much more complicated. He emphasized the uniqueness and complexity of each individual's genetic makeup. Evidence suggests multiple migrations and dispersals, and the mixing of gene pools. The reliability of ancient DNA claims is questioned. The book then described the ancient site of Oligasali in Kenya, where Acheulean tools were manufactured for 1 million years. The purpose of these tools remains a mystery. Bryson mentions the extinction of the dodo bird and other large animals due to human impact, suggesting that humans may be inherently detrimental to other species. In the book, he gives examples of animals that were hunted or killed due to human interests. Also mentions the activities of collectors like Lionel Walter Rothschild, who sent people around the world to gather specimens for his collection. He emphasized the ignorance of humanity in caring for life on Earth and the devastating impact this has had, suggesting that humans have only just begun to understand the importance of protecting and preserving the planet's biodiversity. The author highlights the need for humans to take more responsible actions in order to prevent further extinctions. In 1781, Herschel discovered the planet Uranus but wanted to name it George. Mass and weight are different for a physicist, with weight varying depending on distance from a massive object. Earth's mass and weight are generally considered the same. Some books disagree on the details of James Ussher, who determined the beginning of Earth, and his name is spelled differently in different sources. Darwin provided an exact number of worms in an acre of soil, 53,767. The second law of thermodynamics states that energy is always wasted and perpetual motion devices are impossible. Planck had a tragic life, losing family members and his home in a bombing. Einstein received the Nobel Prize for theoretical physics after waiting for 16 years. The constant c for the speed of light is derived from Latin for swiftness. Doppler discovered the phenomenon of sound waves changing pitch, known as the Doppler effect. The Hubble constant measures the rate of expansion of the universe. The Earth's interior has multiple layers, and the discovery of extremophiles suggests life could exist in extreme conditions. Oxygen is not combustible, but it facilitates combustion of other objects. Cumulus clouds have well-defined edges because of the boundary between the cloud and the dry air. The term thermohaline circulation has multiple meanings in different contexts. Ambergris, found in sperm whale stomachs, is used in perfumes. There are 22 amino acids, but only 20 are necessary for life. The taxonomic classification of humans is complex. Low-temperature washing machine detergents may not effectively kill bacteria. The number of cells in the human body varies, but one estimate is 10,000 trillion. Leeuwenhoek was friends with the artist Vermeer may have used a camera obscura, though no such device was found among his belongings after his death. Antony van Leeuwenhoek, a secretive lensmaker, was the executor of Vermeer's estate. On the same day as Vermeer's birth, Abraham Lincoln was born in Kentucky. Darwin correctly guessed that Chambers had made revisions to the 6th edition of Vestiges, indicating his knowledge of the book. In 1861, at the height of controversy, workers in Bavaria found the bones of an Archaeopteryx, providing evidence for evolution, but it was not considered conclusive. Harvard University Press cancelled the publication of The Double Helix due to complaints about its characterizations. Junk DNA is used in DNA fingerprinting, which was discovered accidentally by Alec Jeffreys. Dubois, a Dutch scientist, was from Isden, a town bordering the French-speaking part of Belgium. Humans, traditionally called hominids, are now known as hominins. Absolute brain size does not determine intelligence. Relative size is more important. Neanderthals and Cro-Magnons may have had different numbers of chromosomes, resulting in reproductive complications. Thank you so much for watching this video. Your support means the world to us. If you enjoyed it, don't forget to give it a thumbs up and share it with your friends. We'll see you in the next video.